At the end of the last video, I said I was going to keep up the component-wise description of our inverse square field because we were going to use that to calculate the curl of an inverse square field. And then I realized that was a little bit silly because it's not necessary. Because we have previously proved that inverse square fields are conservative. And we also proved that the curl of any conservative vector field is 0. So thus the curl of f, where f is our inverse square field, is 0. Now notice that's 0 the vector. Remember, curl is itself a vector field. So it's a vector valued function. If I have a conservative vector field, and inverse square fields are just examples of conservative vector fields, then it's going to be a constant vector valued function that always spits out the 0 vector. Okay. Now, in the last video, we proved that the divergence of f, where again, f is our inverse square field, was 0. Now, that's 0 the number. Divergence is always a real valued function. So, if I have an inverse square field, the divergence is just the constant real valued function that always spits out the number 0. For this, we did need to prove that by looking at the individual components of our inverse square field. This is not true of all conservative vector fields. Curl of a conservative vector field is always the 0 vector. Divergence of a conservative vector field is not always going to be 0. This is something that is true of the particular case of an inverse square field. Okay, but it's kind of neat. If you have an inverse square field, both curl and divergence are 0. They're just different versions of 0. One is a vector, one is a constant number. Okay, now I want to just spend the rest of this section or this video briefly mentioning some other things that are in your textbook that you're not really going to be responsible for. So the textbook introduces you to the Laplace operator. That's denoted as just del squared, and they interpret that squaring as a dot product. So this is just dotting the del operator with itself. And since the components of the del operator are just the partial derivative operators with respect to x, y, and z, if I do this dot product, and of course I can't interpret this as real multiplication, I'm simply applying this operator to this operator, that's giving me actually a new operator. What we're going to get is the sum of the non-mixed second partial operators. So this would be the operator that takes the non-mixed second partial with respect to x. This would be the operator that takes the non-mixed second partial with respect to y. And this would be the operator that takes the non-mixed second partial with respect to z. The Laplace operator simply adds all of those up. Now, this does have some interesting applications, but they're not applications that we're exploring this semester in this class. So you may very well encounter this in some later classes. The book is basically just introducing you to it. I'm not going to hold you responsible for knowing this definition. If you need to work with it in a homework problem or on an exam or a quiz, I would give you the definition and you'd just be working with it at that point. Okay. So you don't need to worry about memorizing that definition. All right, the other thing I want to mention is that the book has a small section in 16.5 where it's talking about Green's theorem. Now, Green's theorem is section 16.4, which we have temporarily skipped. We're going to go back and cover Green's theorem at the end of the semester. So, at this point, I would advise you not to read the section on Green's theorem because it's not going to make sense because you don't know what Green's theorem is. But some of you may, at some point, once we've covered Green's theorem, go back and read that section in 16.5, and I just want to point out that the book is making a bad notational choice. Green's theorem applies in two space. So in Green's theorem, we would have a vector field in two space. So there would just be two component functions. So essentially my vector field is the component function p, which would be a function of x and y, that many copies of I, plus q, which again is a function of x and y, that many copies of j. Now, if that's a vector field in two space, we can't take curl of it. What we can do is we can embed. Remember, this hooked arrow means that we're going to embed in three space. When we do that, we create a related vector field, which I'm going to call f tilde. We simply keep the first two component functions. I'm just now going to view those as functions of x, y, and z just doesn't happen to show up in the formulas. And then I throw on a third component function of 0. So this becomes p copies of I plus q copies of j plus 0 copies of k. Now, if I'm just adding 0 to what I had over here, you might say those are the same, but they're not, because in two space there is no k. This third term that I'm adding, even though its value ends up simplifying to 0, this doesn't make any sense in two space. Now, it's totally legitimate to study certain properties of f by studying those same properties of f tilde. But f and f tilde are not the same vector field. Unfortunately, your book does not show this formal embedding, and they call this vector field f. So they write that they're taking the curl of f, and it looks like they're taking the curl of a vector field in two space. That's a poor choice of notation. It's actually just incorrect. So I'm going to hold you to a higher standard. You're not allowed to do that. If you want to study something in two space by embedding it in three space, you need to actually create a different name for the objects that you're working with in three space. We will do that together when we study Green's theorem later on this semester. But I just wanted to point this out, that I'm going to hold you to a higher standard than our textbook maintains in this, so that if you do go back, or if you're just glancing through things and you're like, wait, they're taking curl of a vector field in two space, I thought Carla said you couldn't. You can't. The book knows that. They've made a notational choice that is very misleading, because they're using the same name f for two different vector fields. I wish they didn't do that, but they do. So I just wanted to call that to your attention for those of you who do ultimately read that section of the book.